Good day everyone and welcome to another video lecture. We are already on lesson 4 and in this lecture I will be teaching you some of the basic process units and their material balances. You will be encountering some of the mostly used unit processes and you will learn how to perform specific calculations for each of them. The core of this discussion would be to give you more and more examples with solved solutions so that you will get acquainted on how to perform specific material balances for specific process units. Okay, so let's begin. Let's start with one of the most commonly used unit process, that's the mixer or the blender. In a mixer or a blender, you have one or more input streams being combined to form one output stream. So that could be you are combining two streams to form one output stream, or you're combining more than two streams to get one output stream. For mixers, there are no chemical reactions, but would oftentimes result in a change in composition. Of course, there will be a change in composition because that's the purpose of a mixer, that is to mix two or more streams with different compositions to arrive with a certain stream of a different composition as well. You have already been acquainted with how a mixer works, but just to review, let's draw a flowchart for a mixer. So for a mixer, or for a mixing process, the mixer is the name of the unit process. Okay, so this is a mixer. You have an input stream, we can label this as A or as B, and then you have an output stream, which is the products or the P. Okay, that's an example of the mixer. Next, we have a splitter or a divider. Sorry. We have a splitter or a divider. The splitter is the opposite of the mixer. However, in a splitter, whatever's the composition of the input stream, that would also be the same composition for the output streams. You can have more than one output stream, but you can only have one input stream for that to be called as a splitter. So again, there are no chemical reactions in a splitter. So let's try to draw a splitting process. So for a splitting process, the name of the unit is a splitter. You have one incoming stream, let's call that the feed, and then you can have more than two output streams. So I can call this as P1 and P2 and P3 and so on and so forth. How many output streams does the problem require? The special thing about the splitting process is that whatever's the composition of your feed, that would also be the composition of your P1, P2, and P3. That's because you're not exerting any effort to separate the components. You're simply splitting the stream of the feed. So it's just like dividing the flow rate of the feed. Okay? The composition in should also be the same as the composition output. That's how a splitter works. Let's continue. Dryer. Okay. You already know what a dryer is. A dryer is a device that aims to remove moisture or to remove a certain solvent out of a substance. So we are acquainted with the common process of drying in the drying of clothes after washing them. You might also be familiar with the drying of rice before it's milled and other processes involving drying. You have two types of dryers. The first type is a direct heating dryer, wherein a heating element inside the equipment heats the substance and in turn, the substance gives off some of its moisture content. These types of dryer, you only have your feed as your inlet, and your outlet would be your dried products and the water or the water vapor removed. The removed water vapor is not allowed to stay inside the dryer because it will affect the drying rate of the substance inside. As soon as the water vapor is formed, it is removed from the dryer. So how does that look in a process? Okay, so we have here the drying process. As I've told you earlier, there are two types of the drying process. I will show you both. The first one is the one described in the slide. Your input is the wet substance, that is your feed. Your main product is the dry substance, and you have another output stream, which is the water. Let's call this W. The water here is water vapor. Unless you condense it, then you have liquid water. Okay, this is the first type of drying process wherein you have a direct heating element. The second type of dryer uses hot air to get the moisture from the substance. So this is the process for the second type of dryer. Sometimes we call this convection dryers, or we call them air dryers because we use hot air. We have the feed, we have the product. The feed here is the wet material or the moist material. The product is the dried material. And what are we using to accomplish this drying? We are using hot air. So one of your inputs is the A1. I'll call this the hot air. And of course, as air goes in, it must go out. And that is one of your outputs. I'll call it A2. This is your output air or outlet air. The outlet air carries the moisture that was taken out of your feed. Okay? We will not yet be discussing this second type of dryer because this involves calculation involving gases with one condensable component, which is water vapor. This will be tackled at the end of the term. So for now, the drying process would involve this type, the one with the direct heating element. Let's proceed. Filter. You already know what a filter is or what the filtration process is. So this is one of the easiest unit processes. What happens is this is a separation process wherein solids suspended in a liquid or gas are removed by letting the suspension pass through a filter. Your unit process here is a filter. The feed is the suspension or the mixture of solid liquid or solid gas. And after it passes through a filter, you have two outlet streams. The first stream is the residue, that's the solid. And the second stream is the fluid phase. It's either the liquid or the gas phase, and that's called the filtrate. One stream goes in and two streams goes out for a filter. Oftentimes, we normally do not represent filter as its own process unit, or we do not represent filter as its own box. We normally incorporate filter inside of processes. For example, crystallization. Crystallization processes normally have a built-in filter. Next, evaporator. The evaporator is also a type of dryer wherein the goal is to drive off excess solvents in order to get a more concentrated solution. Water is evaporated from a solution, resulting in the concentration of the solution. So what does the evaporation process looks like? The evaporator receives the feed. The feed normally is a solution. The solvent can vary. It can be water, it can be an organic solvent. You have one product, or should I say you have one major product. This major product is more concentrated than the feed. And you have a byproduct. In this case, the byproduct is your solvent. In many of the cases that you will encounter, the solvent is water. So we label the stream W. But again, you can label the streams with whatever letter you want as long as you understand it. Okay? So that's the evaporation process. Next, crystallizer. Crystallizer balances are oftentimes one of the most difficult to handle because there are two processes happening, or sometimes three processes happening in one. You have the crystallization itself. You can also have filtration because, as I've said earlier, filtration is sometimes built inside of your crystallizer unit. And sometimes to achieve the crystallization, you need to remove some of the solvent, so that could also entail evaporation. So if we combine evaporation, crystallization, and filtration into one process unit, then that would be sometimes complicated. Okay? The main theory behind crystallization is that a solution, which is oftentimes saturated, is cooled down to reach supersaturation. Wherein, if you have a supersaturated solution, that is an unstable solution and it has a tendency to remove some of its excess solute by crystallizing. Okay, then the crystals are then filtered out and are removed as a product. So oftentimes, this is coupled with a built-in filter to separate the crystals from the solution. That's what I have said earlier. What does a crystallizer unit looks like? For the crystallization process, so we have here the crystallizer. For the most basic crystallization process, you have your feed, which is again oftentimes a saturated solution or a solution that nears saturation. This enters at a specific temperature. We will call that the temperature of the feed. And it then exits as a crystal. The crystal is the crystallized parts of your solution. And then you also have another output stream, which we shall call the ML, or the mother liquor. Now, some curious things about this mother liquor. The mother liquor is almost always a saturated solution. But you might ask, why is the mother liquor a saturated solution if the feed is also a saturated solution? As mentioned earlier, we are normally carrying out the crystallization process by changing the temperature of your feed in order to encourage some of those crystals to grow out. So if your feed enters at a temperature of TF, then the mother liquor exits at a temperature of TML, in which case, almost always, the temperature of the mother liquor is less than the temperature of the feed. This is, of course, we want to obtain as much crystals as possible, so you have to lower the temperature of the solution. So you might have noticed that the crystals and the mother liquor are already separated from each other, and that's because this crystallizer unit has a built-in filter. It's understood that we have a filter here that is combined with the crystallizer, and that lets us to separate the crystals from the mother liquor. Remember, the mother liquor is the remaining fluid or the remaining solution after we have obtained the crystal. Okay, this is the shortcut solution. Another way of taking a look at crystallization processes is that you have two units. The first unit is the crystallizer, and the second unit is the filter. What happens is your feed goes in through the crystallizer, and you lower the temperature of the feed, and that results to the crystallization of some of the salts. And then your output of the crystallizer is called the magma. We shall call that M. The magma is the combination of the crystals and the saturated solution or the mother liquor. And of course, we want to separate that because you might want the crystal for the product or you might want the saturated solution for the product. That's why we have the filtration here to separate this into the crystal and into the mother liquor. Basically, it's the same process between the two of this, but the first one, this one uses two units, while the second one uses only one unit, which it incorporates both the crystallizer and the filter, and that shortens our solution. Okay, so you might want to use the second one. Next, absorption tower. Okay, absorption tower is where liquid gas or vapor liquid absorption happens, or sometimes even stripping. The process of vapor liquid absorption includes you have something you want in the vapor stream or in the gas stream that you want to be dissolved in the liquid stream. So it's It's a type of recovery. Let's say, for example, you have a toxic substance in the gas phase or in the vapor phase that you don't want to get out of the process. So we introduce a liquid or a solvent that can dissolve the toxic substance so that your vapor or your gas stream exits the process without a trace or with very, very little traces of the toxic substance. Okay? In gas liquid absorption, a soluble component of the gas stream is transferred or absorbed into the liquid stream. But this could also happen the other way around. You can also have an evaporating solvent coming from the liquid phase and it joins the gas phase. In that case, that's known as stripping. So stripping is the opposite of absorption. How does that look in a process? Okay, let's see. In the evaporation process, normally we are utilizing towers, and we call that the absorption tower. In the absorption tower, we have four streams. You have two streams for the liquid and two streams for the gas. Keep in mind that those two streams will be in contact with each other, but they will not mix because they are two separate phases, one's liquid, one's gas. Okay? And for clarity purposes, we shall be illustrating the two different phases in two different directions. The liquid phase will be coming from the top to the bottom, and the gas phase will be coming from the bottom to the top. So let's say, for example, you have an entering vapor or an entering gas. We will call that V1. And your remaining gases, which are not soluble in the solvents, will be exiting the column, and we will be calling that V2. Okay? Your absorbent will be entering from the top. This is your liquid phase. We will call that L1. And your absorbing liquid together with the absorbed species would combine together and exit the bottom of the tower, which we shall call L2. This is the basic uh, flowchart of an absorption process. Okay, you have four streams. You have two inputs and two output streams. In this instance, it's just a matter of exchanging components. No, one of the component of the gas phase could transfer to the liquid phase, or one of the component of the liquid could transfer to the gas phase. We shall be having some examples of this later. Next, okay, we have covered some of the most common uh, processes that you might encounter for single units or for single process balances. Now we shall be dealing with some of the examples. We have here 9 examples which I will be solving for you. And then after this, at the end of this lecture, you will have your worksheet number 2 wherein you will be trying to solve them on your own. Okay, let's begin. Example number 1. A stream A containing 30 weight percent ethanol and 70 weight percent water is blended with stream B containing 60 weight percent ethanol and 40 weight percent water. The product contains 35 weight percent ethanol. Determine the ratio of the two input streams A over B. Okay, we now have here the given. So I have written here our flowchart. Your process here is a mixing process as stipulated by the problem, and the process unit is the mixer. Okay, you have two streams, A and B, or two input streams, which will be mixed together to form one output stream, which is stream B. Okay, how do we do this? We list our required. The required from the problem is the ratio of stream A to stream B, or the mass flow rate of stream A divided by the mass flow rate of stream B. You have noticed that we are only given compositions, or we are given all compositions, but we were not given any of the flow rates of those streams. If this is the case, you could actually specify as your basis one flow rate, or sorry, the flow rate of one of the streams. It's your choice if you want to specify the flow rate of the products or if you want to specify the flow rate of one of the input streams. But one thing's for sure is that when you set your basis, you cannot set more than one basis. You can only set one basis, and that basis is the flow rate of one of the streams, and you cannot set two flow rates of streams because then you would arrive with the wrong answer. Okay? For this problem, let's try to set as my basis, uh, let's use A. I will be using 100 kilograms per second of A. What happens if we set that basis? When we set that basis, we basically are giving away the value of A. But we still have to determine the values of B and P, which will be solved coming from the value of A and coming from the compositions given. Now, if you choose another basis, would that change the final answer? No? The answer is no, because take a look at your required. The required is a ratio between A over B. If you change your basis to, let's say, for example, 1,000 kilograms per hour of A, you will still arrive with the correct ratio of A over B because the values of B and P will be adjusting depending on the values that you get for A. Okay? So let's proceed with the material balance. You are already familiar with this coming from our previous video lectures. After the basis, we start with our OMB or our overall material balance. In this case, you only have three streams, so this is quite simple. The OMB is A plus B equals P. And since we have specified a value for A coming from our basis, this balance would now be 100 plus B is equal to P. This is our first equation. We have two unknowns, that is B and P. Those are both flow rates. So in order for us to solve for any of those values, we need to get one more equation so that we'll have two equations, two unknowns. I have also mentioned earlier that to make calculations simpler, you have to look for a tie component. In this case, we don't have a tie component because out of your two components, which are ethanol and water, both are entering from two streams and exiting from one stream. Therefore, there's no tie component. So it will not matter whatever component you choose for your component balance. Let's use ethanol. So if we performed an ethanol balance, what should we have? In stream A, we have 30 weight percent of ethanol. That would be mathematically represented as 0.3 times A plus in stream B 0.6 B and sorry and in the product you have 0.35 P. That is our ethanol balance. But we have a value of A. Let's substitute. You have 0.3 times 100 plus 0.6B equals 0.35 P. This is our second equation. You will notice our second equation also has two unknowns, and that's B and P. Therefore, we can simultaneously solve our two equations with two unknowns in order to yield both the values of B and P. You can do this manually. You can substitute P is equal to 100 plus B into equation number 2 so that you can get the value of B. But you can also do this in your calculator straight. Okay, so let's use our calculators. Let's use this calculator in our screen. So if you want to solve for two equations, two unknowns, you simply go to mode 5, 1. For the first equation, we have, let's use x as B and y as P. We have 1 for A, B is negative 1, and then C is negative 100. For our second equation, we have 0.6, negative 0.35, and then your constant is negative 0.3 times 100. Okay, so your x is, again, our x is the B, so this is 20 kilograms per second. And then P is 120. And then you need to take a look at your problem and ask yourself, does it make sense? Does it make sense that if we add A and B, we get P? So A is 100, B is 20. We add them together, we get 120. So our answers make sense. To answer the required, we want to get the value of A over B. So this is 100 over 20. So this is 5. Our ratio of A over B is equal to 5. That means that that stream A is 5 times larger than stream B. Okay? So you can also try this example with different bases, and you will see that you will be arriving with the same A over B ratio. Even if you choose a peculiar basis, like let's say, for example, you try to resolve this problem, but you use your basis as 562 kilograms of P. You start with the products, and then you back solve, you can solve the values of A and B. You should be arriving with the same A over B ratio if you have the correct answer. Okay, so that's a relatively simple problem for mixing. Let's go to the next one. Mm, okay, next problem. A liquid mixture containing 45% benzene and 55% toluene by mass is fed to a distillation column. So from the first sentence itself, you already know that your unit is a distillation column. The overhead product contains 95 mole percent benzene, and the bottom product leaves with 8% of the benzene fed into the column. The volumetric flow rate of the feed stream is 2,000 liters per hour, and the specific gravity of the feed mixture is 0.872. Determine the mass flow rates of the distillate and bottoms, and the composition of the bottom stream. Okay, I have already drawn the flow charts and the given. Let's take a look. So to recap this problem, again, we have a distillation column. The feed to the process is 2,000 liters per hour of a mixture of benzene and toluene, wherein benzene is 45% by mass or by weight, and toluene is 55% by weight. The specific gravity of the feed mixture is 0.72. Let me verify. Sorry, that's 0.872. Okay. Specific gravity 0.872. It's also mentioned in the problem that your distillate is 95 mole percent benzene. So you see here we already have a discrepancy in reporting compositions. The feed is in mass percent and your distillate is in mole percent. And the bottoms, it says in the problem that it contains 8% of benzene coming from the feed. The statement in the bottoms product does not imply that your bottom contains 8% by mole of benzene. This is different. So we are not talking about composition. We are simply talking of how much percent of the benzene coming from the feed ends up in the bottoms product. And the answer is 8%. Okay? So do not get confused with those statements from the problem. We are required to solve the distillates bottoms flow rate, that's D and B, and also we are required to solve for the composition of B. Okay, so let's start our solution. For our solution, we start with the basis. If you take a look at the flow charts, you can already find your basis. Our basis will be coming from the feed. That's 2,000 liters per hour. So that's a volumetric flow rate. And you know that if you're given a flow rate, then you can use the time as the basis. Okay. So our basis here is 1 hour of operation, such that we already have a value of F, which is 2000 liters. The problem is your feed composition is given in percent by mass. So we have to convert our feed to mass in order for us to apply the composition. Lucky for us, we are given the specific gravity of the mixture. What does a specific gravity of 0.872 mean? We can get a value of the density of the feed here, and if you already have the value of the density of the feed, you can convert from volume to mass. Okay? So if the specific gravity is 0.872, this implies that the density of the feed is 0.872 grams per ml, or if we want to have an easier calculation, we can also represent this as 0.872 kilograms per liter. You can try converting it, and it would result to the same value. Okay, we are choosing to use the units kilograms per liter because your feed is in liters, and we can simply convert it to kilograms. Okay, so let's convert. You simply multiply 2000 liters of your F, multiply with the density 0.872 kilograms per liter. We have, that's 2000 times 0.872. Okay, you have 1744 kilograms of the feed. Once we have that value, we can now start with the material balances. Okay, let's begin. For the material balance, we again start with the OMB, the overall material balance. Your OMB in this case is F is equal to V plus B. Okay, we again have come to a crossroads to how we can approach this problem. Our main problem comes from the fact that your distillate is in mole percent, while your feed is in mass percent or in weight percent. The easiest way around this is you simply convert your distillates to a mass percent, and we can then carry on with our OMB. Or you can convert your feed to a mole percent, and we can carry out with the OMB because again, there's no chemical reaction, so you can perform the OMB with either mass or mole units, it doesn't matter. But it's way easier to convert the distillates to mass percentage compared to converting the feed to mole percentage because we already have the mass of the feed. Okay, so let's have a little floating calculation here in which where we will be aiming to solve for the mass composition of stream D. Okay. For these mini calculations, it's okay for us to have mini bases because the mini bases here will not be affecting our overall solution. Now, you might be asking, I have mentioned earlier that you cannot have more than one basis for a problem. No? What I was talking about then was the main basis. In this case, our main basis is 1 hour operation and we cannot change that. But for mini calculations like this, it's perfectly fine to choose a mini basis just for us to convert from mole percent to mass percent or vice versa. Okay? Let's choose a mini basis for D. The most convenient basis in this case is 100 moles because D is in percent by mole. That means that we now have 95 moles of benzene and 5 moles of toluene. Okay? Next, we simply determine the molecular weight of benzene and toluene and list them in this table, convert them to mass, and then later determine their mass composition. So molecular weight, mass, in kilograms, and then mass percent. Okay, that is our mini calculation. The molecular weight of benzene is, so benzene is C6H6, that is 12 times 6 plus 6, 78 grams per mole. And then toluene is C7H12, H8, that is 12 times 7 plus 8, 92. Okay, and then we simply multiply for benzene, that is 95 times 78, 7410 grams, but we want to convert this to kilograms, so this is 7.410 kilograms. For toluene, that is 5 times 92, 460, 0.46 kilograms. The total is 7.87. And then you simply divide the mass of benzene to the total number of mass to get the percent by mass. So we have 7.410 divided by 7.87. That is 94.16%. And then for toluene, that is 0.46 divided by 7.87. That is 0. Sorry, in percent, that is 5.84%. So you see, with this mini calculation, we were able to determine the mass composition of stream D. So let's now write here in D, you have 94.16 weight percent benzene and 5.84 weight percent toluene. And then you can now delete the floating calculation. Well, in my case, we are deleting the floating composition because we don't have enough space in our board here. But in the exam, you keep all of your floating solutions so that you can have a backup to your solution. Okay? So we're done with the F, we're done with D. Let's take a look at the bottoms product. It says here the bottoms contains 8% of benzene from F. So how do we do that? Let's have another round of mini calculations. In stream F, which is 1,744 kilograms, it composes of two components. The first component is, of course, benzene. The second component is toluene. Benzene is 45% of the feed, and toluene is 55% of the feed. In the statement of B, it contains 8% of benzene from F. We can simply calculate that as the benzene in B is equal to 0.08 or 8% of the benzene from F. But the benzene from F is only 45% of F. So we simply multiply 0.08 by 0.45 times F. And F is 1744 kilograms. That is how we determine how much benzene is in B. Okay, calculating 0.08 times 0.45 times 1744, we have 62.784 kilograms of benzene in B. Okay, so let us again write this here in B. So we have two components in B. But we do not know how much toluene is in B, so we are going to leave that blank. Okay, well anyway, we just need to get the value or the mass of B. Okay? At this point, we can now proceed to our OMB because everything now is in mass. Okay, going back to the OMB, you have F equals D plus B. We already know F, so this equation becomes 1,744 is equal to D plus B, equation number 1. Next, component balance. What component is the easiest to balance in this case? You only have two components, that's benzene and toluene. You don't have a tie component, so you have to choose between benzene and toluene, but it would be easier if you solve using benzene because benzene already have a value of mass in the bottoms product. And toluene, we don't have any value, so we cannot solve the problem. Okay, So let's perform the benzene balance. So how do you write your benzene balance? In the feed, that is 0.45 F, but F already has a value. So let's already substitute. 0.45 times 1744 equals, in the distillates, we will be using the converted mass percents. That's 94.16. So that's 0.9416 of D, plus in the bottoms product, we already have a mass. That is the 62.784. So in our benzene balance, we only have one unknown or one variable, which is D, which we can solve from here now. Okay, solving for D, we have that is 0.45 times 1744 minus 62.784 divided by 0.9416. Okay, your D is 766.8. Oh wait, how many significant figures should we have? So let's go back to the problem. Okay, count how many significant figures should we have? We have three, 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 three. We will count this as four. This is okay. So we will be using three significant figures. So it should only be 767. The distillate is 767 kilograms per hour because our basis is 1 hour. Okay, so we are done with D. Next, to solve for B, you simply substitute the value of D back to your OMB because by then you will only have one unknown. So if you substitute, what do we have? You can calculate the value of B as 1744 minus 767. You have 977 kilograms per hour for B. Next, composition of B. So how do we determine the composition of B? If you go back here, so let's highlight this one. So by subtraction, that would be 977 minus 62.784. Or let's just have it as 62.8 because we're using three significant figures. Your toluene is 914.2. Okay. But we are after for the composition of B. So let's have a small box here. So in B, you have 62.8 kilograms benzene. You have 914.2 kilograms toluene. And then if you convert that to percent by mass, you simply divide the mass with the total. So for benzene, that is 62.8 divided by 977. That is 6.43%, three significant figures. And then benzene. And then for toluene, you simply subtract that from 100 or 1 because this is mass fractions. For toluene, you have 93.57% toluene. Significant figures, 93.6. Okay? So we are done with problem number 2. We have calculated the flow rate of D, B, and the composition of B. I hope that you have found some interesting tips and tricks in this problem. For example, the use of the mini basis or the use of some floating calculations just to complete our flowchart or to complete our given. Okay, next. Okay, next problem. It is desired to prepare a sweetened concentrated orange juice. The freshly pressed juice contains 5% solids, and it is desired to increase this amount to 10% by evaporation. Calculate the amount of water that must be evaporated based on 100 kilograms per hour of fresh juice. Okay, again, I have already drawn the diagram for this problem. Okay, so we have this one. Based on the problem, our process is evaporation and the unit is an evaporator. So in the evaporator, you have one feed, that is your fresh orange juice, containing 5% solids and 95% water, flowing at 100 kilograms per hour. And you have two products. First is your concentrated juice, that's your 10% solids and 90% water. And your byproduct is pure water, which is water vapor evaporated coming from the juice. Okay? We are required to determine how much water is evaporated. Am I right? Okay. The required is W. We want to know how much water can we, or how much water should we evaporate to achieve the desired product. In this case, that's the 10% solids juice. Okay, basis. In this case, we are given a mass flow rate of the feed, 100 kilograms per hour. Therefore, your basis is 1 hour operation. That gives us a value of F, 100 kilograms. Next, OMB. Your overall mass balance in this case is F, which is your lone input, is equal to your two outputs, P plus W. We are already given a value of F, that's 100. Therefore, the equation becomes 100 equals P plus W. That's equation number 1. Next, component balance. Do we have a tie component? Okay, take a look at the flow chart. You have two components there, and those are water and the solids. If you take a look at the water, water comes in at F and goes out both at W and P, so it's not a tie component. However, the solids only enters at F and only exits at P, therefore it's a tie component. So let's write here, your tie component is the solids. So let's perform the tie component balance, solids balance. Okay, so this is 5% of F, 0.05 times 100 is equal to 0.1 times P. There is no solids in W, so we leave that. So based from this equation, we can already solve for the value of P. Solving, so the 5% of 100 is 5 divided by 0.1. So P is 50 kilograms per hour. So you can only imagine here how much or how difficult it is to concentrate orange juice. Imagine your fresh orange juice came in at 100 kilograms. Then after concentrating, you are only left with 50 kilograms of the concentrated juice. Okay? And based on our required, we are required to solve how much water is evaporated. Therefore, you simply substitute the value of P to our OMB. You can get the value of W also as 50 kilograms per hour. That is our final answer. Significant figures, let's check. This is three significant figures, and 4. Therefore, we are required to keep 3 significant figures in our final answer. So we answer 50.0 kilograms per hour of evaporated water. So this is somewhat of an easy problem. No? Normally, evaporation problems are easy. You just have to use the solids as your tie component. Okay, next. In a flour mill, wheat is to be adjusted to a moisture content of 11.4%. If the whole grain flour arrives with 15% moisture by weight, how much water must be removed from 250 pounds per hour of fresh wheat by drying? So the next process is the drying process, and our unit here is a dryer. Okay, so for this drying process, we have the following diagram or the following flow charts. I have already listed all of the given. The fresh flour is at 15% moisture, and the remaining presumably are solids. That's 85% solids. The flow rate of the fresh flour is 250 pounds per hour. Your desired product should only be at 11.4% water, and the balance would be the solids. So let's determine the balance. That would be 100 minus 11.4. That is 88.6% solids. If you take a look at our diagram, it looks very much like the evaporation or the evaporator unit. No? We have one input, that's the feed, and we have two outputs, that's your dried product and your evaporated solvent. In this case, it's water. So we know that we also have a tie component here, and that is the solids. So let's balance the solids later. We are required to determine how much water must be removed. Okay, so we want to determine the flow rate of W. So let's start with the solution. What is your basis? The basis would again come from the mass flow rate of the feed, that's 250 pounds per hour. Therefore, a very good basis is 1 hour of operation. That gives us a value of F of 250 pounds. Okay, next, OMB. F equals P plus W. We have a value of F that is 250 equals P plus W. That's equation number 1 for your OMB. Next, component balance. We can use the tie component, which is the solids. So for your solids balance, what do we have? 85% of the feed is equal to 88.6% of P. Okay, solving for P, we have, so this is 0.85 times 250 divided by 0.886. Okay, so your P is 239.84 pounds per hour because our basis is 1 hour. Okay, but we are looking for the value of W. So you substitute this to your OMB. You can solve for the value of W as 250 minus 239.84. And we have the following results. That's 10.16. Let's take a look at how many significant figures should we have. This is 3 significant figures. This is also 3. This is 4. Okay, let's use 3 significant figures. That is 10.2 pounds per hour. So that's how much water will be removed from 250 pounds per hour of fresh flour in order for us to achieve the desired dried product. Okay, the solution looks very much like the evaporator. Next problem. So for number 5, raw potatoes are about 25% starch and 75% water. Before frying, raw potatoes are peeled and then washed. Assume that 8% by weight of the potatoes are lost during peeling. Potatoes are then dried to 7% total moisture content. What is the mass of dried potatoes produced from 100 kilograms per day of raw potatoes? Okay. So this problem potentially can be a multiple unit problem, but we will not do it as a multiple unit problem. Obviously, the unit process involved here is a dryer because we are drying the potatoes prior to frying. But we also need to peel the potatoes wherein 8% of the total weight will be removed. So we will already be factoring that out so that we can avoid the use of multiple units. Okay? Okay, let's see the diagram. Okay, so I have listed here the given. For your feed, you have 25% starch, 75% water. We want to dry that to only 7% water and 93% starch. If you take a look at the given flow rate in the feed, that's only 92 kilograms per day, wherein the given is 100 kilograms per day of raw potatoes. But it was also specified that 8% would be the peel. So if you subtract the 8% of 100, which is 8 to 100, you only get 92 kilograms per day of potatoes without the peel. Okay, so we have already included that calculation in our givens. Now this is just the same as the previous problem. We just have to set our basis. By the way, what is the required value? The required value is the mass of dried potatoes produced. So that is the P. We are solving for P. Okay, next, what is your basis? We are given a flow rate of the feed, therefore our basis is 1 day of operation. We always go for the denominator. Next, OMB. Your OMB here is the same. F is equal to P plus W. We're already given a value of F, that is 92. So that's 92 is equal to P plus W, equation number 1. Again, we have a tie component here because your stream W only contains water. Therefore, the starch is a tie component. So let's perform the tie component balance. Starch balance. What do we have? 0.25 of F, which is 92, is equal to 0.93 of P. Solving for P, we have 0.25 times 92 divided by 0.93. So here's our answer. How many significant figures? We need 2 significant figures, so that is 25 kilograms per day. So imagine if you are manufacturing potato chips, you are buying the raw potatoes. Let's say, for example, you have 100 kilograms of raw potatoes. After peeling them and after drying them before frying to make potato chips, you only have 25 kilograms remaining of your potatoes. So a large part of the potatoes is just water, which is lost via drying. Okay? So this is a very easy problem. Let's proceed to the next one. This is a harder problem. This involves crystallization. Okay. Let's first internalize the problem. 300 kilograms per hour of a saturated aqueous KCl solution at 60 degrees Celsius is fed to a crystallizer where it is cooled down to 20 degrees Celsius. After the crystals were formed, a built-in filter separates the crystals from the mother liquor. It was determined that 250 grams of the saturated solution is adhering to every kilogram of the crystals. How much crystals are produced per hour? If the mother liquor is just disposed, how much KCl is wasted? The maximum solubilities of KCl in water at 60 and 20 degrees Celsius are 45.8 and 34.2 grams per 100 grams respectively. So there's a lot going on here. So let me just summarize the problem in a diagram. Let's see the flow chart. Okay, so this is our crystallizing process or the crystallization process. You see here that the feed is 300 kilograms per hour of the saturated solution at 60 degrees Celsius. Your product, first, the crystals, there's no amount specified, but it's stated that for every kilogram of crystals, there is 250 grams of saturated solution at 20 degrees Celsius adhering to those crystals. So that gives you somewhat of a complicated composition, but we will decode that later. And your mother liquor is a saturated solution at 20 degrees Celsius. We are given the maximum solubilities of potassium chloride in water at 60 and 20 degrees Celsius, and that's given in the table. So our task here is to somehow convert all of these values into mass fraction values that we can use for our material balance. So how do we do that? We will be doing that by the use of mini bases. So let's not first get into our required. We will not yet be performing any material balance. Let's just be uh, let's just perform some mini calculations in order to determine the mass compositions of the streams. Let's start with the feed. In your feed, you have a saturated solution at 60 degrees Celsius. And if you take a look at this table, at 60 degrees Celsius, your maximum solubility is 45.8 grams of KCl per 100 grams of water. Now, this is the technique for crystallization problems. We somehow have to find a way on how to convert this ratio into a mass fraction or to a mass percentage. The way we do that is to create a mini basis. So what is a good mini basis for crystallization problems, especially if you're given solubility data? Always take a look at the denominator. In this case, your denominator is 100 grams of water. Therefore, my mini basis is 100 grams of water. So this tells us that your F, or the feed, contains two components. First, you have the 100 grams of water, and you also have 45.8 grams of KCl. If you put it this way, then it becomes really obvious and it becomes really easy on how we can convert this to mass fractions or to mass percentage. We simply get the total. The total mass for F would be 145.8 grams, and you can get the mass percent. For KCl, that would be 45.8 divided by 145.8. So I will be writing this in terms of percentage. So this is 31.41% KCl. And then the water, you simply subtract this to 1. 68.59%. See, we have converted from solubility data to mass fractions or to mass percentage. So we can now write this mass percentage into our flowchart. So I will write here 31.41% KCl and 68.59% water. So let us highlight this one so that we will know that it is you have calculated for these values. Next, the mother liquor. So let me erase this mini calculations for F. In the mother liquor, it's a saturated mixture, but it's at 20 degrees Celsius. If you take a look at the solubility of KCl at 20 degrees Celsius, it's lower. So we can again use that as basis for our mini calculations. So in the mother liquor, again, setting a mini basis of 100 grams of water. And if the solubility in the mother liquor is 34.2 grams of KCl per 100 grams of water, that means that in your mother liquor, you have 100 grams of water and 34.2 grams of KCl. The total mass of mother liquor is 134.2 grams. Okay, let's convert this to mass percentage. That would be 34.2 divided by 134.2. That is 25.48% KCl. 25.48% KCl. And then subtract this from 1, 74.52% water. Okay, we can now write this here. 25.48% KCl, 74.52% water. Okay, so those are our obtained values simply coming from solubility data. Okay, so let's erase this. Okay, we're done with the feed. We're done with the mother liquor. Now, take a look at the crystals. So, in brief definitions, the crystal is simply the solid form of your solute. Your solute in this case is KCl, so you expect the stream C to compose of KCl crystals. However, it contains adhering solution. The adhering solution in this case comes from the mother liquor because remember, when crystallization happens, the crystals and the mother liquor are together in a same container, so they are mixed together, but they are filtered, so you can get your crystals and your mother liquor separate. But there's an adhering solution, and that adhering solution comes from the mother liquor. Thus, it has the same composition as the mother liquor. So for stream C, we will be having a little bit of a different mini calculation. So let's see. If you take a look at the given in stream C, you have 250 grams of saturated solution per 1 kilogram of crystals. Therefore, a good mini basis in this case would be 1 kilogram of crystals. That means that you have 1 kilogram of dried KCl crystals. Okay, so let's dissect C. We now have 1 kilogram, or I will be using grams. So I now have 1,000 grams of KCl. This is obtained as the crystal. And based on the ratio, I should have 250 grams of the saturated solution. I will also be calling this the mother liquor. So we have 250 grams of adhering mother liquor. Now, based from our previous computations, we know that the mother liquor contains 25.48% KCl and 74.52% water. So we can apply that in here. You can further split your mother liquor into water and KCl. So let's do that. 250 grams of mother liquor, multiply that with 0.2548. You have 63.7 grams KCl, and the remainder would be water. So that is 250 minus 63.7. We get 186.3 grams water. So you see here, we only have one entry for water, but we have two entries for KCl, this one and this one. So you just have to add them, and then you can get the percentage by weights. So let's rewrite your 3 for C. How much water do we have? We have 186.3 grams of water. For KCl, we have 1,063.7 grams KCl. Total amount, how much is this? 1063.7 plus 186.3. Okay, 1250 grams total. Okay, now we can solve for the mass percentage. So 186.3 grams of water divided by 1250 grams total mass. The mass percentage of water in the crystals is 14.90%. And then get the balance, you get the mass percent of KCl. That is 85.1 or 85.10%. So with that technique, we are able to convert everything in here into mass percentages, which will be useful for material balance calculations. This is 85.10% KCl and 14.9% H2O. Sorry, that is KCl. Okay, now we are ready to perform the material balances. This solution that I shown you is normally the best solution to tackle crystallization problems. You convert everything first to mass fraction before you proceed to your material balances. Okay, basis. The basis in this case is 1 hour operation because we are given the flow rate 300 kilograms per hour. Next, OMB. The OMB is feed equals crystals plus mother liquor. One input, two outputs. Next, component balances. Do we have a tie component? If you take a look at your two components, KCl and water, they are present in all of the streams. Therefore, you don't have a tie component. So you can use either a water balance or a KCl balance to complete your solution. Let's go for a KCl balance. So our KCl balance would be, in the feed part, 0.3141 times 300 is equal to, in the crystals, 0.851 times C plus in the mother liquor 0.2548 ml. The calculator is obstructing. Okay. So that is our KCl balance. So from your OMB, sorry, we forgot to substitute. This should be 300 is equal to C plus ml. This is your first equation. And then for your KCl balance, that is your second equation. We have two equations, two unknowns. You use your calculators to determine the values of C and ml. So solving 1 and 2, what do we get? So let's go to the calculator. First equation, we will be letting C as X and ML as Y. So this is 1, 1, 300. And then next is 0.851, 0.2548. And then the constant is 0.3141 times 300. Okay. Your crystals, 29.84 kilograms per hour. Your mother liquor, 270.16 kilograms per hour. So, let's take a look at the significant figures. This is four significant figures. Temperatures are not counted in this case. This is four significant figures. This is 3, 3. Okay, we will be using three significant figures for the final answer. Therefore, this would be 29.8 kilograms per hour and 270. So this is our answer for letter A. The amount of crystals produced is 29.8 kilograms per hour. Okay, next, letter B. The question for letter B is, if the mother liquor is just disposed, how much KCl is wasted? Okay. If we take a look at the mother liquor actually contains a significant amount of KCl. It's about 1/4 in weight, not 25.48%. So the mother liquor is 270 kilograms per hour. If we take the 25.48% of this, that is how much KCl we are wasting if we will just throw away our mother liquor. So let's see. If we take 0.2548 times 270 kilograms per hour, the result would be 270 times 0.2548. Our result is 68.8 kilograms per hour of wasted KCl. If you take a look at this value, the wasted KCl is even bigger than the KCl that we have obtained from the crystals. The crystals is only 29.8 kilograms per hour. And it's not even pure KCl, it's only 85% KCl. So if you throw away the mother liquor, you are wasting a large amount of the KCl. In typical crystallization processes, after we have cooled down the feed to obtain the crystals and the mother liquor is not disposed. No? What happens is the mother liquor is fed to an evaporator. What happens to an evaporator is some of the excess water will be evaporated such that your mother liquor would now be more concentrated and at a higher temperature such that we can recycle the mother liquor back to the feed. You can cool it down and you can obtain more crystals. That is an example of a recycle problem, and later on during this term, you will be taught how to deal with recycle problems. Okay, but for now, this is how we answer crystallization problems. Okay, next, I think we have one more. I think we have one more crystallization problem. So we'll see. Next problem. Okay. Number 7. It is desired to recover ammonia from a gas stream composed of ammonia and nitrogen gas by contacting with an absorbing solvent. The inlet gas stream contains 10 weight percent ammonia, while the inlet liquid stream is 100% solvent. Both inlet streams enter at a rate of 1,000 kilograms per hour. If 98% of the ammonia is absorbed, what are the flow rates and composition of the two exit streams? Okay, so we have here the diagram. Okay, if you take a look at the given, so we have an absorption column as our unit. We have two inlets to the process, that's V1 and L1. V1 is your vapor stream that's coming into the process, and L1 is your liquid stream coming into the process. V1 is composed of 10 weight percent ammonia and 90 weight percent nitrogen, while L1 contains 100% pure solvent. We shall call the solvent S. Now, your two exit streams, V2 and L2, we have deduced that V2 will contain ammonia and nitrogen. Our first assumption here is that your solvent is non-volatile, meaning it will not evaporate to join the gas stream. And another observation here is The problem states that only 98% of the ammonia will be absorbed by the solvent. So the remaining 2% of the inlet ammonia would exit as a vapor in V2. Okay? The required are the flow rates and composition of V2 and L2. So let's begin the solution. Our solution here would start, as always, with the basis. A very good basis here is 1 hour operation because we are given the two flow rates of V1 and L1, which are both 1000 kilograms per hour. So therefore, we now have V1 as 1000 and L1 is also 1000 kilograms. Next, OMB. Our OMB is V1 plus L1 equals V2 plus L2. We have two inlet streams and two outlet streams. Next, component balance, or you can already substitute the values of V1 and L1 in your OMB. So our OMB would become 1000 plus 1000 equals V2 plus L2. Therefore, our OMB reduces down to 2000 equals V2 plus L2. That is our equation 1. Okay. Next, component balance. We have three components in this system. You have the nitrogen, the ammonia, and the solvent. If you take a look at our given, can you spot any tie components? The tie components would be entering on one stream only and exiting at one stream only. So for instance, the easiest tie component to spot here is the solvent. The solvent S only enters in L1 and it exits at L2. So let's perform the solvent balance. For the solvent balance, input is 1000. The output is how much S is in L2. Therefore, we now know that the amount of S or solvent in L2 is also 1000 kilograms. So let's write here S in L2 is 1000 kilograms. Next, the problem stated that 98% of the ammonia coming in V1 will be transferred to the liquid stream. So that is as good as saying that 98% of the ammonia present in V1 will be transferred to L2 because L2 is the exiting stream of the liquid. So how do we determine that? How much ammonia is in V1? So V1 is 10% ammonia and we need to get 98% of that. So in a mathematical equation, the 98% of the 10% of 1000 will be the amount of ammonia that is transferred in L2. So if we calculate that, 1000 times 0.98 times zero point 0.1, that is 98. The ammonia in L2 is 98 kilograms. We can write it here, 98 kilograms. So we are done with L2. We just have to transfer to V2. So let me just mark this. Sorry. So let me just mark this. These are the values that we have already determined. Next, you can also see that the nitrogen gas or N2 is another tie component because it only enters at V1 and it exits at V2. So therefore, if you perform a nitrogen balance, nitrogen enters at V1, that is 90% of 1000, and that exits as the nitrogen in V2. The nitrogen in V2 is 900 kilograms. Let's write it here, 900. Next, how much ammonia? So earlier, we stated that 98% of the ammonia is transferred to the liquid phase. Therefore, the remaining 2% will be left in the gas phase. So the 2%, so let's represent it this way. So the amount of ammonia remaining in V2 will be uh, 10% of V1 times 2%. So that will be 1,000 times zero point 0.1 times 0.02, which is 2 kilograms. Therefore, we only have 2 kilograms of ammonia remaining in V2. Let's highlight that. Okay. So basically, we are already done in solving the problem. We just have to address what is really required. So the required are the flow rates and composition. So let me erase this. For the compositions, let's start with V2. So in V2, you have two components, the ammonia and nitrogen. We can easily get its percentage by weight. The total weight of V2 is 902 kilograms per hour because our basis is 1 hour. And for the mass percentage, that would be for ammonia 2 divided by 902. Okay, that's 0.22% weight percent. And for nitrogen, that is the balance, 99.78% weight percent. Next, in L2, for L2, we have also two components. You have the solvent and the ammonia. The total, the total value for L2 is 1,098 kilograms per hour. And the compositions would be 1,000 divided by 1,098. The solvent is 91.07%. And then ammonia will be the balance, 8.93%. Okay, so there we have it. We have determined the flow rates of V2 and L2 as well as their composition. This is a template solution for absorption problems. So if you encounter another absorption problem, you can employ this same solution. Okay, next. Okay, next example. This is another absorption problem. So let's see if we can analyze this problem correctly. An absorber is used to remove acetone from a nitrogen carrier gas. The feed, with an acetone weight fraction of 0.213, enters at a rate of 200 kilograms per hour. The absorbing liquid is water, which enters at a rate of 1,000 kilograms per hour. The exit gas stream is 0.8 weight percent acetone and 2.9% water vapor. We are also assuming that this is weight percent. Okay? Determine the acetone mass fraction in the bottom stream. So we want to determine the mass fraction of acetone in the exiting liquid stream. That's what we mean by the bottom stream. Okay? So this is a little bit similar with the previous example. I have already laid out one example for absorption. What I want you to do is to answer problem number 8 as part of your problem set number 2. Okay? Let's take a look at the next number. Number 9. Okay. The solubility of barium nitrate at 100 degrees Celsius is 34 grams per 100 grams of water, and at 0 degrees Celsius is 5 grams per 100 grams of water. If you start with 100 grams of barium nitrate and make a saturated solution in water at 100 degrees Celsius, how much water is required? If the saturated solution is cooled to 0 degrees Celsius, how much barium nitrate is precipitated out of the solution. The precipitated crystals carry with them on their surface 4 grams of water per 100 grams of crystals. So this is the same as our previous example in KCl. So number 9 here would be number 2 in your problem set number 2. Okay, to recap, your problem set number 2 would contain two items. That's number 8 and number 9 in this PowerPoint presentation. So this is to practice your problem solving skills. By the way, for all of the worksheet and problem sets that I am giving, I would also be uploading a sample solution for that after the expiration of the deadline so that you can study if you're correct or if you're wrong. Okay? After this, okay, this is now your worksheet number 2. Worksheet number 2, only 3 problems. These are very easy problems. Number 1 is just a verification process. Number 2 is evaporation. Number 3 is mixing. So these are very basic problems. Okay? I might combine worksheet 2 with problem set 2. Okay? So we will see. So you need to answer worksheet 2 and problem set number 2. And from now on, all of the lectures will be given at the start of the week, and then all of the problem sets and worksheets will be submitted at the end of the week. So that's it for this lesson. I hope you've learned something and keep safe.